Yeah. Oh wait, that might be.
Hey.
We're gonna have a lecture tomorrow, or not tomorrow, sorry. Wednesday.
We're gonna have a review session Wednesday. Yeah, so today will be the last day of new content, and then Wednesday we'll just review. Hey guys. Yep. Wait a second.
Do you happen to be doing research or pioneering research?
I have some students working on stuff right now. Usually the way I usually do my research here is that I make all the project student focused. And so I have the students kind of come up with their own project and I mentor that. And so I don't have any kind of long-standing project right now that people are working on, but if you're interested, we can chat probably after the semester when things calm down. Yeah.
Oh, that's just.
V versus what position? No position. What was velocity?
I'm gonna be honest with you. And you guys have. Well, I mean, is that the velocity profile? Oh, wait. This is. No, I don't know. And even that. I don't know. It's like a 2-hour walk. And that's why I go like. Well, not you. Are those the exams?
Those are the midterm exams. If you haven't picked it up yet, you can pick it up.
Yeah. Wait, I think you're the best. Did you do from 7 years to another? Because the way that I understand the organizer, she's going from no years to years. That's how she got it.
Yep. Yeah, you can go ahead and pick it up. Yeah. Mhm.
But it's like it's honestly, it's so that was I keep on, bro, I'm like taking that. Which I look at this. It's easier to do this in like less than 24 my mind's like, if I can get to this portion. I got steam. See, I have this mentality, I guess, when I didn't start on one portion. It's 2 hours. Not for me, like how I also like talking. This one works good enough. Yeah. I did that when it was because I decided to do this. You guys are global self. Here's the thing, I remember And then I go back to this. Yeah. So if I can,
You guys.
Into one, depending on that full row, single row, right.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone, with the final week of lectures. So how's everyone doing today? Tired? Yeah, it's that time. I know. Okay, so we have just one more set of lecture notes today. So I have a couple examples I want to do today. This should help you out with problem 4 on the homework, hopefully. Okay. And then just like I mentioned last week, Wednesday will be our review session. Okay? So today will be the last day of new content. Wednesday we'll review. And then as you can see from the screen right now, our final exam will be next Wednesday. Okay? So before I start today, I want to go over just some logistics for the final exam. Right? So the final exam will be next Wednesday, May 18th. It's going to take place between 3 and 4:50 p.m. So about almost 2 hours. It's going to take place here in this room, E201. And so just like the midterms, there's no plans to offer it virtually. And so, please show up in person. And in terms of what you can bring, it's very similar to the midterms. The only difference now is that, because, there's more content, it's going to be a longer exam. You can bring 2 cheat sheets. Okay? So you can bring 2 8.5 by 11 sheets of notes. You can write whatever you want on them. You can write on both sides. Obviously, you can't put the exam questions or the exam answers on there, but hopefully that's going to be impossible. And so, but besides that, you can put whatever you need. Okay? So besides that, you should bring your writing utensil and a calculator as well to help you with some of the calculations. Okay? In terms of the format, the format will be very similar to the midterms, except just a little bit longer. And so there's going to be 6 short answer questions. And so that's up from 4. So typically our midterms have 4 short answer questions. And there's going to be 4 problem solving questions, right? And so that's a little bit higher than average. So I believe our first midterm, we had 2 problem solving questions. And on the last midterm, we had, the first midterm, we had 3, last midterm, we had 2, and the final exam will have 4, okay? And just as always, I recommend that you start your studying with the study guide. And so, I put that together last Friday. And I curated it quite a bit. And so, not everything that we covered this semester is on that study guide. So, before you start studying, I would definitely look at the study guide because, that's going to tell you what to study. And if it's not there, then it's going to tell you what not to study as well. Okay. And I was very thoughtful with the study guide. So, I wanted to cut down the list quite a bit for you guys. So I think overall I cut down maybe 5 weeks worth of content from the study guide. And so we'll have about 2/3 of, you'll be responsible for about 2/3 of the semester's worth of content for the final exam. Okay. So make sure you look at that before you start studying. I'm saying that a lot of times because, I do this every semester where I put the study guide out and I curate the list, but then someone's always going to come to me after, it's like, oh, I studied this, but it wasn't on the exam. And I was like, yeah, you should have looked at the study guide. I put it out there and I said it like dozens of times. So, use the study guide to guide your study. Okay. Because I know you guys, this is just one, I know this is just one exam of many that you guys are taking. I know you guys are doing a lot of final projects as well. So I want to make sure that the time you put studying for this class is as efficient as possible. Because practically speaking, even for a 2-hour exam, it's impossible to put everything that we covered in this semester on the exam. And so, I want to be kind of upfront with you guys about, what a reasonable amount of information that I can put on a 2-hour exam like this. Okay. All right. And so, are there any questions on the final exam format or just anything before we start today? Yep.
You sent out the poll already for the final review.
Yep.
We're gonna do it on Thursday.
Wednesday. Yes. Yeah. Yeah. We're gonna do the final review on Wednesday. Yeah. Wednesday with the review session. My question is the study guide posted? Yes. Yeah. I posted it. I posted it last Friday. I believe I linked it to the email that I sent to everyone. But I'll put it. I don't think I haven't updated the page for week 16 yet. I'll put it on the page for week 16 too. Yeah. And so before you vote on the poll, take a look at the study guide too, because I only made stuff on the poll if it's on the study. All right. Any other questions about the final or anything before we start today? Okay. All right. So let's go ahead and start. Okay, so last week we were going over this idea of radiation exchange, right? In particular, we were kind of halfway through the subject of what I call gray body radiation exchange. And so the idea behind this unit is that, whenever you have two bodies and they're radiating heat, and, almost all bodies will radiate heat, all bodies will radiate heat, then they're going to exchange heat with each other via radiation as well, okay? And this is granted that they can see each other, right? And so, what we've been discussing a lot in radiation is that optics, or how electromagnetic waves and and all that stuff, that's playing a much bigger role. Okay? Okay. And there are two main factors that that can affect this radiation exchange. Okay. And so the first factor, well, I would say there are two impediments, I should say, or two resistances that that can impede radiation exchange. Okay. And so the first is view factors. Okay. And so if you recall from last week, view factors are this idea that when a certain object radiates on another object, not all of the radiation from one object is going to reach the other one, right? So it depends on how far they are apart from each other, what their shapes are, and so on and so forth. Okay. And so we can sum that up with what I call like a view factor resistance. Okay. I'll just call it RV for now. Okay. So RV is 1 divided by the area multiplied by the view factor. Okay. And let's just assume we have two surfaces here. Okay. So we have A1, F12. Okay. And that's the inverse of that. So we've already done problems regarding this, right? And so if you look at problem 3 on the homework, you look at the examples that we did last week, we saw how view factors can affect radiation and how we can factor those into our calculations. What we haven't done yet is how do we factor in surface properties, okay? And that's where the gray body part comes into play. Because as we've been talking about, not every single surface is a perfect radiator, right? And so depending on what the surface looks like or the surface properties, that's going to have an effect on how much radiation it gives off. Okay? And so this presents another form of resistance, okay, where this one is dependent on the emissivity. Okay. And we had an expression for the resistance that's given by that. Okay. Remember, emissivity is what we call epsilon, and that's a coefficient between 0 and 1 that tells you how good that surface is at emitting radiation. Okay? And so at the maximum, epsilon can equal 1, and so that's what's called a black body, and so that's the maximum of what you can radiate, or it can be down to 0 even for a surface that doesn't radiate any heat at all. Okay. And so to solve these problems, we're going to take these two expressions. And I've described them as resistances, very deliberately, because we're going to take a thermal circuit approach to solving these radiation problems. All right. And so I have a couple examples today to kind of illustrate this process. So one example where it is a little bit simpler, and the second example is a little bit more complicated. All right, but for now, that was just a kind of a recap of what we went over last Wednesday. So are there any questions on this? Okay, all right, so let's go ahead and jump into the examples then. All right, so for this first example, let's look at our concentric cylinders. And so we have a cylinder, an outer one just like that, and we have an inner one just like that. Okay? And we'll assume this inner cylinder is solid, so there's no fluid flowing on the inside. Okay? So we'll call the inner cylinder, we'll call that surface 1, and the outer cylinder is surface 2. Okay? And what we're interested in computing is the radiation exchange between 1 and 2. Okay? Okay. Right. And so you should recognize this. And so this is an example we did last week, but this time we're actually going to compute the radiation exchange. Okay. And the other big difference here is that neither of these surfaces are going to be perfect surface. Okay. So they're going to have an emissivity that's less than 1. Okay. All right, so let's put some numbers on this. And so let's go with surface 1 first. And so the temperature of surface 1 we'll assume is 600 degrees Kelvin. Okay. Epsilon 1 will be 0.8. And the diameter of 1 will be 10 centimeters. Okay. Surface 2 will have the following properties. Okay, so surface 2 is also going to have a temperature, an epsilon, and a diameter. And so temperature 2 is going to be 400 Kelvin. Epsilon 2 is going to be 0.7. And diameter 2 is going to be 20 centimeters. Okay. And just for the sake of simplicity, these are cylinders, and so you can assume that they're going into the page. And so we're going to assume that they have a length of 1 meter going into the page. Okay. All right, so before we go about solving this, let's just go ahead and talk just what we generally expect to happen. And so we can see here that the inner cylinder, surface 1, is at a higher temperature than the outer cylinder 2, right? And so, generally what we expect, just like all the rules of heat transfer, is that we're going to have a net movement of heat or net movement of energy from surface 1 to surface 2, okay? And so let's keep that in mind as we go and solve the problem. All right. And so in this problem, we're interested in computing radiation exchange. And so, just like any kind of thermal circuit type problem, our first step here is going to be to draw the thermal circuit. And here, and for these types of problems, it's going to be even more important because, we're not going to have just simple straight circuits anymore. For this one, we will, but for the next example, you'll see that the circuit is going to split off into multiple paths. And so, drawing the thermal circuit here is going to be even more important than before. Okay. So we have our end nodes here. And let's go ahead and count the resistances that we should have. Okay. And so we'll assume that the left-hand side here will be surface 1, and the right-hand side will be surface 2. Okay. Okay. And so if we're going from surface 1 to surface 2, the first thing that we're going to pass by is the emissivity resistance of surface 1. Okay. Right, and the way that you can think about that is if heat's going to pass from surface 1 to surface 2, the first thing it has to get past is the fact that surface 1 does not have a perfect surface. Okay, and so that's going to be the first thermal resistance that we're going to encounter. Then, as the radiation leaves surface 1, the next form of resistance it's going to encounter is the view factor resistance, okay? Because now we're transferring from surface 1 to surface 2. And so this resistance right here will be 1 divided by A1, F12. And then the last resistance that we're going to encounter. So as the radiation, crosses that space between surfaces 1 and 2, it's now going to land on surface 2. But surface 2, surface 2 is not perfect either. And so it's not going to absorb all the radiation that comes at it. And so we have another emissivity resistance. Okay? And so this is going to be 1 minus epsilon 2 divided by A2 epsilon 2. Okay. All right, so we have a 3 resistance system, right? So we have 2 emissivity resistances, one for each surface, and then we have a view factor resistance, in between the surfaces. Okay. Okay. And so when you're drawing these thermal circuits, you can use that rule of thumb, right? And so for each surface that you have, you should automatically draw a resistance for it that has to do with its emissivity. And then anytime you're transferring in between surfaces, you're going to have a view factor resistance for that as well. Okay. And so if you follow those 2 simple rules, then you can draw the circuits for these, and you're going to be off to a good start for these kinds of problems. Okay. All right. So before we move on to the next step, I'm going to go ahead and draw in the radiosities. And so you probably see me draw these 2 dots here. And so I'm going to call that one J1, and I'm going to call that one J2. Okay. So remember, the radiosities account for both, the radiation that comes off of the surface and any radiation that reflects from it as well. Okay. And so that should be the second step that you do after you draw your circuit, is to draw the radiosity nodes in there. Okay. And the radiosity should always occur right after your emissivity resistances. Okay. And the last thing I'll do before we start to solve this is I'm going to go ahead and draw on the black body radiation or black body emissions. And so at the end nodes, we'll have sigma. It's just 1 sigma. We'll have sigma T1 to the 4th. And then on the other end node, we'll have sigma T2 to the 4th. All right, so that's our starting point. And so, from this circuit, we're going to be able to solve for, solve for everything that we need. Okay. Any questions on this, on how the circuit was set up? Okay. All right. So I spent a bit more time on this just because these circuits are even more key here. And so if you kind of start off with a bad circuit, you're kind of digging yourself a hole. And so spend some time, make sure that your circuit looks good before you start. Make sure that you're consistent with all the rules. So all the surfaces have their emissivity resistance, and all the proper view factor resistances are accounted for as well. Okay. Here it's pretty simple, just because we just have 2 surfaces, but you'll see in the next example when we have 3 how this can be a lot more complicated. Okay. And so the next thing that we're going to do, our next task here is to compute the 2 radiosities. Okay. And so we're going to need to compute J1 and J2. All right, and to do this, the way that we're going to do this is we have 2 unknowns here, right? So we have two J's that we need to solve for. And so we need to set up a system of equations, right? So we need to develop 2 equations to solve for these 2 unknowns. Okay. And the way that we're going to use our circuit here is we're going to use what's called it has so many different names, but it's essentially going to be a Kirchhoff's current law. Okay. But in this situation, it's going to take the form of basically conservation of energy. Okay? And I'll show you what I mean by that in a second. So we're going to apply. Okay, so we're going to apply conservation of energy at the radiosity nodes. Okay. And so what do I mean by that? So what do I mean by conservation of energy? Let me show you how I do the first one first, and hopefully that'll make things a bit more clear. So I'm going to consider this, whoa, hell. Okay. And so let's consider radiosity node 1 first. Okay, so this is the node J1. Okay. And so remember, this circuit here is transferring heat, right? And so heat is being, moved throughout the circuit. Okay. And so if we focus on just one of the nodes at a time, then what we can say is that, we're going to have some heat that's coming in this node. Okay, so there's going to be heat in. Okay. And we're also going to have some heat coming out of this node as well, right? Because the heat is just moving through the circuit. For this particular problem, since we know that temperature 1 is greater than temperature 2, we know that this is the direction that the heat's going to flow, right? So generally, you know that heat's going to go from the left to the right here, right? Because we know heat's going to flow from surface 1 to surface 2. But I'll show you later that the direction of the arrows actually don't really matter all that much. And so, as long as you're kind of consistent with how you form these expressions, the only thing is that the arrows just have to be there. And so if you get the direction of the arrow wrong, it doesn't really all matter all that much, okay? And so what we're going to do is that, now that we have these expressions Q in, heat in and heat out, actually, let me give them symbols. Okay? And so I'll call heat in, we'll call that Q in, and the heat out, I'll call Q out, okay? Let's use the circuit to come up with equations for these. So let's start with Q in. So Q in is coming from the left, and it's crossing over this emissivity resistance here, okay, and then going into J1. And so Q in right here, what we can say is that Q in is going to be sigma T1 to the 4th. Okay. We're going to subtract the radiosity there, and so this is going to be minus J1. And this is going to be divided by the resistance in between them. So the resistance in between them is 1 minus epsilon 1 divided by epsilon 1 A1. Okay. So that's the heat coming in. The heat coming out is going to be going the other way. Okay, so Q out. Okay, we're going to consider the nodes that are downstream of this. And so we have J1 minus J2, okay, because J2 is the closest node to J1. And we're going to divide this by the resistance in between. So in between J1 and J2, we have 1 over A1 F12. Okay. Right. And so if we consider just the J1 node right here, that's the amount of heat that's coming in and the amount of heat that's going out. Okay. And so by conservation of energy, right? Conservation of energy is saying that energy can't be created or destroyed. It can only be transferred from one form to the other or moved from one place to the other, right? What we say is that these two have to be equal to each other. Okay. Okay. And so if these two have to be equal to each other, then we can set their equations equal to each other as well. Okay. And so what we have is sigma T1 to the 4th minus J1 divided by 1 minus epsilon 1 divided by epsilon 1 A1 Okay, this is equal to J1 minus J2 divided by 1 over A1 F12. Okay. Okay. We have a bunch of parameters here that we already know the values of. Okay, and so let's go ahead and plug in. Okay. So we know what sigma is. Sigma is just the Boltzmann constant, and so we've known that, you know, for the last few weeks now. T1 is given to us in the problem. Epsilon 1 is given to us in the problem. Okay. A1 wasn't directly given to us, but, you know, we know how to compute the surface area of a cylinder. Okay. And so surface area of the cylinder is going to be pi d1 times L. Okay. And the other factor that, and the other thing that we don't know yet is F12. Okay. But, you know, if you remember from our past example, or even if you don't remember, we can logic it out again. Okay. F12 is the view factor between surface 1 and surface 2, right? Let me just show you how I computed this real quick. And so since we only have two surfaces here, we know that F12 plus F11 is going to be equal to 1, right? But what do we know about F11, right? So by inspection, we know that F11 has to be equal to 0, right? Because we have a convex surface. And so there's no way for surface 1 to radiate on itself without bouncing off something else first. Okay? So we know that F11 is going to be equal to 0. So that means F12 is going to equal to 1. Okay, and this is by inspection. Okay. All right, and so if you plug everything in, you know, the only unknowns that you're going to have left are going to be J1 and J2. Okay, so we have two unknowns, but that's okay. You know, this is only just the first equation. And so if we plug everything in and then we work out, you know, we kind of simplify things, and, you know, I'm going to skip a lot of that plugging in stuff. But if we plug in and we simplify, we get the following equation. And so we have 9,234.17 is equal to 1.57 J1 minus 0.314 J2. Okay. Okay. And so this right here, we'll call it equation 1 of 2. Okay. All right. And so that's the process you're going to take to come up with these. You can call them radiosity equations. Okay? And so from the circuits, you know, you're going to apply conservation of energy, or you can call them Kirchhoff's current laws at the nodes, and you're going to use that information to develop these radiosity equations. Okay? And so this is the first equation, and so we're going to do basically the exact same process at another node, and so that's going to give us another equation to solve for J1 and J2. All right, any questions on how we obtained this equation here? Okay. Okay, so that's the first one. And so I'm going to do the exact same thing, but apply it at the other radiosity. Okay, so the other radiosity, and be nice to red, green, colorblind people. Okay. And so our other radiosity node there is J2. Okay, so we're going to do the exact same thing. And so we're going to have Q in. Okay, we have Q in and Q out. And so we're going to compute Q in and Q out based on the nodes in the circuit, and then we're going to set them equal to each other. Okay, so this is radiosity node 2. All right, so let's do Q in first. So Q in, we've actually computed up here already. So we can say it's J1 minus J2 divided by 1 divided by A1 F12. And so this right here is Q in. And then Q out is going to be on the other side. So on the other side, we have J2 minus sigma T2 to the fourth divided by 1 minus epsilon 2 divided by epsilon 2 A2. Okay, so this right here is Q. Okay. And so we can go ahead and plug in and simplify again. Okay. And so we plug in and simplify, what we get is 2,128.04 is equal to 1.78 J2 minus 0.314 J1. Okay. We'll call this equation 2. Okay. All right. So now we have two equations, right? So we have two equations and two unknowns. Okay. Now the hard part is solving for this system. Okay? So now we turn into a linear algebra class, at least for the next 10 minutes or something. Okay, and so any questions on this before we set about solving it? Okay, all right. So we have just a very basic linear system of equations. I say it's basic, but these are probably among the lowest on the list of favorite types of problems to solve in all of mathematics. Okay, because these types of problems are not that hard, but they are extremely annoying to solve. And so I know that there's a lot of different ways that you can solve it, and so I would say just kind of pick your favorite way. But the way I usually like to solve these is I use one equation, I solve for one of the unknowns, and then plug that into the other equation. Okay. All right, so let me write that down. Okay. Okay. Right. So I know this is one form of you can do this. Another way you can solve these problems is to do the equation addition, right? And so I know that's taught. But I think for a two equation system, I think this kind of makes the most sense. And so with that, to that end, let's take equation 1 and solve it for J2. So we solve equation 1 for J2. We have J2 is equal to 1 divided by 0.314 times 1.57 J1 minus 9234.17. Okay. Right. So now that we have this expression for J2, let's plug this into equation 2. Okay. And so we plug into equation 2, then what we get is 2128.04 is equal to 1.78, right? 1.78 times J2, and so let's go ahead and plug in the expression that we have up there for J2. And so it's going to be 1 divided by 0.314 times 1.57 J1 minus 9234.17. Okay. And then this is minus 0.314 J. Okay. Yep. No, this is from equation. Yeah. Yeah, we plugged it back into equation 2 after that. Yeah. Mhm. Yeah, you could have easily done the other way too. So it's up to you. It's up to you. You can always flip a coin if you're not sure. Right? So I remember doing that before. Or you can roll a dice, whatever you want. Okay. All right, so this is kind of a mess. Okay, and so it's definitely not the cleanest equation. But if you'll notice, the only unknown that we have left is J1. Okay. And so if you work through the algebra here, you can solve this for J1. And so just because I want to make sure I get through the second example, because that one's more closely related to the homework, I'm going to go ahead and jump right to the answer. Okay. And so if you solve this equation here for J1, you get J1 is equal to 6,344.59. And the units for radiosity are going to be same as heat flux. And so it's going to be watts per meter square. Question, can we use calculator to solve this on the exam? Yeah, if your calculator is capable of solving systems equation, you can definitely do that. So that's the other way. So you can definitely set this up as a matrix set of equations and solve it that way. I kind of forgot that calculators can do that nowadays. Typically I use I usually set these up in MATLAB and solve it the same way. But if you're comfortable with solving these in the calculator, definitely you can do that. Okay, so now that we have J1, we can go ahead and plug this back in and solve for J2. Okay. As we plug this back in, then we get J2 is equal to 1 divided by 0.314 times 1.57 times the J1 we just computed, so that's 6,344.59, okay, minus 9,234.17, okay. And so we compute that, we get J2 is equal to 2,314.74 watts per meter square. Right. All right. And so the last step in this process is to compute the radiation exchange. So now that we have the radiosities, this is fairly simple to do. Okay? And so the radiation exchange, we'll call it Q12. Q12 is going to be equal to J1 minus J2, which we just computed, divided by the resistance between them. And so there's going to be 1 divided by A1, F12. And so we have all of these quantities. And so it's going to be 1,266.04 watts. All right. So that example, I know we kind of spent a bit of time on it, but that kind of shows you, the process that you need to follow for these types of problems. So typically, your first step is always going to be to draw the thermal circuit. Once you have the thermal circuit, you're going to use that thermal circuit to compute the radiosities. Then from the radiosities, you can use that to compute the radiation exchange, or in other words, the radiation heat transfer between the surfaces. Okay. All right, and so in this next example, we're going to follow that same process. It's just that it's going to be a little bit more complex because we have 3 surfaces instead of just 2. Okay, and of course, this is more consistent with your homework, but the homework also has 3 surfaces. All right, any questions on this? Okay, all right, so let's do one more example today, and this will be the last example or last example of new content that we'll go over in this class. Okay. And so in this example, let's consider two parallel plates that are exposed to the larger environment. Okay. And so we're up here, we have plate 1, or excuse me, that's plate 2. So down here we have plate 1, plate 2, okay? And so we have two plates and it's exposed to a greater environment, but we're going to use the same trick that we did last time. And so we're going to close the system. And so, I'm going to draw a dotted line here. Okay, I'm going to draw a dotted line here. And so even though, we drew two dotted lines here, but we're going to make the assumption here that both of those dotted lines are at the same temperature. Okay? And so that's going to be T infinity. Okay. And so both the dotted lines together, because they're at the same temperature, we're going to consider them as one. Okay. And so those will be surface infinity, surface infinity. And so that helps us out a bit, right? And so instead of considering 4 surfaces, we'll just consider 3. Okay. All right, so let's put some numbers on this. And so we have T1 and epsilon 1 here. Okay, so T1 is going to be 800 Kelvin. Epsilon 1 here will be 0.8. Okay. For surface 2, we're going to have T2 is equal to 600 Kelvin. Epsilon 2 is going to be 0.6. We have T infinity. It's going to be the same on both sides. And so T infinity here will be 300 Kelvin. So it'll be about room temperature. And epsilon infinity. This is typically the case. And so, typically whenever you have to draw kind of imaginary lines like this or made up lines, we assume that those imaginary surfaces are going to act as a black body. Okay, so we're going to say that epsilon infinity here is going to be 1.0. And that makes sense, right? And so, because we're basically drawing these dotted lines in space, it doesn't make sense that, if we send some radiation out for it to just randomly reflect back at us, right? And so, that would be really weird. And so what we assume is that, if we send radiation out to the environment, it just accepts it. Okay, so the environment by itself is not going to reflect radiation back at us. Okay. Oh, we need some geometry here. And so we'll say that the separation between these, call this H. And so the separation between the surfaces will be 1 meter. And this length right here, okay, the horizontal length, we'll call it L. And we'll also say that that's 1 meter. All right. And just like in the previous example, we're interested in, first of all, computing the radiosities. And so that's gonna be our first step, just like last time. But in addition to the radiosities, we're also interested in the heat loss to the environment from both surfaces. Okay? Okay. Right. So, the problem is or the process of the problem is going to be the same. It's just now we have a third surface. And so, that's actually going to complicate things a bit. Our circuit's definitely going to look a lot more scary. But you'll see that it's the process that we follow is still going to be the same. Okay. Any questions on the setup problem? Yeah. Infinity. So that's I'm just labeling that surface. And so we'll call that surface infinity. But you can call that surface 3 if you want as well. Yeah. Let me draw it a bit clear. My iPad kind of acting up right now. Any other questions on the problem before we get started in solving it? Okay. All right. So first step, just like last time, is we're going to draw our thermal circuit. And so now we're going to have 3 nodes in the circuit. Okay? So we're going to have, we'll call this node 1, or excuse me, I'll call this node 2. Okay? Call this node 1. And we'll call this node infinity. All right, so first thing, let's go ahead and label these nodes. And so when I draw these are basically the end nodes in our system. Okay? And so our end nodes are always going to have the black body radiation emission. Okay? So this is going to be sigma T1 to the 4th. This one here is going to be sigma T2 to the 4th. And it's going to be sigma T infinity to the 4th. And so the next thing we're going to draw in is all the emissivity resistances. Okay? So remember, these are resistances of the surface themselves. And so they're all going to have one. Okay. Right. And so these are all the resistances that have to do with the emissivity. So for surface 1, we have 1 minus epsilon 1 divided by epsilon 1 A1. For the second surface, we have 1 minus epsilon 2 divided by epsilon 2 A2. Okay. And then for surface infinity right here, we have 1 minus epsilon infinity divided by epsilon infinity A infinity. And then from here, we need to connect all these nodes together with the view factor resistances. So we're going to have connect surfaces 1 and 2. Okay. And so this is going to be 1 divided by A1, F12. We're going to connect surfaces 2 and infinity. And so this is going to be 1 divided by A2, F2 infinity. And then we need to connect surfaces 1 and infinity as well. So this is going to be 1 divided by A1, F1 infinity. Let's a little bit. P2. Okay. All right. So it's a little bit more intimidating, right? And so that we have kind of a lot more going on. And so all we did was just add one surface here. So the last thing I'll do here is I'm going to go ahead and add in our radiosities. And so we have radiosity 1, J1, radiosity 2, J2, and radiosity 3, J3. Okay. And so all the nodes on the inner kind of the inner loop are now labeled. Okay? J1, J2, J3, or J infinity. I'm sorry. Okay. All right. Any questions on how we drew this circuit here? It looks scary, but just take it kind of step by step, right? So start with the end nodes, then draw in their emissivity resistances, right? Then draw the view factor resistances. And if you just kind of build it up step by step, it's a little bit less intimidating. Okay? And in fact, for this one, we can simplify this a little bit more. Just kind of based on the properties of this particular problem. Okay. So before we go about solving this, we can eliminate one of these resistances right away, right? Because what do we know about surface infinity, right? We know that surface infinity has an emissivity of 1.0, okay? And so if you have an emissivity of 1.0, that means this resistance here is going to be 0, okay? And so if that resistance is 0, that means that this end node and J infinity are just connected by a wire. Okay. And so what this means here, go ahead and circle this. And so if that emissivity is equal to 0, then what we say is J infinity here is going to be equal to sigma T infinity to the 4th. Okay. And so that lets us solve for one of the radiosities kind of right off the bat. Okay. And so we don't need to develop any equations for this. Right. So since we know T infinity, we know sigma, what we can say right away is that J infinity here is equal to 459.27 watts per meter squared. So that's great. And so that solves for one of our radiosities already. So the only thing we have to solve for now is just 2. Okay, so we need to solve for J1. I'll start with that. And then we need to solve for J2 as well. Okay, and so to solve for J1, J2 here, we're going to follow the same process that we did in the last example. And so we're going to sum up all the energies coming in and all the heat transfers going out. So now, this becomes a little bit more difficult, right? Because now we have three coming in, right? And so we need to decide on the directions of the arrows that they're going to go, right? But remember I told you that it doesn't really matter what direction you put the arrows in because all the signs are going to work itself out, okay? And so to prove it to you, I'm going to assume that all of the energy is actually coming in here. All right, so we're going to assume that we're going to have energy coming in from this direction, energy coming in from this direction, and energy coming in this direction, okay? And so with this, we're going to assume that Q in is going to be the sum of all 3 of those guys, okay? Whereas Q out is going to equal to 0. Okay. This might seem, kind of, paradoxical, right? But I'll show you that it's actually okay. Because of the convention that we're going to use. Okay? So let's go ahead and sum up Qn. Okay, so Qn, first of all, we have the contribution that comes from n node 1. Okay? And so that contribution is going to be, and this convention that you should use is that, whichever direction you draw the arrow, okay, you're going to take the direction on the opposite side of the arrow. Okay, and so we're going to look at the tail of the arrow. Okay, so the tail end of this arrow is coming from, the end node here. And so the tail end for that is going to be sigma T1 to the 4th, okay, minus the node that's on the other side of the arrow, or where the arrow is pointing to, which is J1, okay, divided by the resistance between. Okay, so it's 1 minus epsilon 1 divided by epsilon 1 A1, okay? Right, to that, we're gonna add, the contribution that's coming from the top, okay? And so this is the one that's coming from J2. And so coming from J2, we have a J2 minus J1, right? Remember, we start with the direction that's on the tail end of the arrow, okay? So we have J2 minus J1 divided by the resistance between them, which is 1 divided by A1 F1 2. And then finally, we have the contribution from the infinity node, okay? And so we have J infinity, because that's what's on the tail side of the arrow, minus J1 divided by 1 divided by A1 F1 infinity. All right. And so if we set this equal to Q out, what we say is that these three quantities are going to be equal to 0. All right. And so that's going to be our equation 1. So does that make sense about how I chose the convention for that, and which one you should put first, which one you should put second? Okay. And so it doesn't really matter, it doesn't really matter which direction you put the arrows, as long as you use this convention of putting the tail side of the arrow first minus the head side of the arrow, then it's all going to work out. Okay. All right, question in the chat. So question in the chat asks, why Q out equal to 0? And so the reason I did Q outs equal to 0 is because we're summing up all the energies that are coming into this node right here, right? And so to do that, we have to draw arrows, or you don't have to, but it helps tremendously to draw arrows, okay? And so for this particular case, I'm going to say that all the energy is coming in, okay? And so we're going to have energy coming in from node 1, from J2, and from J infinity, okay? And so for this particular case, Q in is going to be these three quantities, okay? But we don't have any Q out, right? And so Q out is corresponding to an arrow that's leaving the node. Okay? But because of how we drew the arrows here, we drew all of them coming in. And I know it doesn't seem like it should work, but because of the convention that we chose with the direction of the arrows, all the signs are going to work out. And in fact, a lot of people, once you kind of get used to this, a lot of people kind of prefer this way of doing it, just so that they don't have to fuss too much about the signs, because all the signs in this way kind of take care of itself. Right. Any questions on? Other questions on this? Okay, so let's go ahead and do the same thing, but we're going to do it for the J2 node. Okay. All right, so just like we did with the J1, I'm going to go ahead and draw the arrows in here. Okay. And just like J1, I'm going to go ahead and draw all the arrows coming into node 2. Okay. So I'm going to draw an arrow this way an arrow this way, and an arrow this way as well. Okay. Okay. All right, so let me just go ahead and do this one really quickly. And so this one is going to be, first we have sigma T2 to the fourth minus J2 divided by 1 minus epsilon 2 divided by A2 epsilon 2. Okay. To this, we're going to add J1 minus J2 divided by 1 minus A1 F12 plus J infinity minus J2 divided by 1 divided by A2 F2 infinity. Okay. And all of this is going to equal to 0. Okay. All right, so these are going to be our two equations, okay? Because we still have two unknowns here because we have to solve for J1 and J2. And so this combined with the green equation here, we can use them to solve for J1 and J2. Well, we can't do that just yet, okay? Because it may seem like we have everything that we need to plug in here, but what we don't have are the view factors. Okay? And so before we can actually plug in to solve for this, we need to find out, what those view factors are. Okay? And so we're going to need to solve. We only need to solve for 3 of them here. So we need to solve for F12, F2 infinity, and F1 infinity. Okay? And so we're going to kind of remind ourselves what we did last Monday, I think it was. Right, so we're going to apply all our rules here to solve for these view factors. Okay. Right. So the next step is going to be to solve for the view factors. Any questions on this? Yeah.
So consider that the arrows were arbitrarily chosen.
Yep.
So we could have done all the arrows going out.
You could. Yep. Yep.
And could we also do like something going in, something going out?
You could. Yep.
Could it just be a mess?
It can, yes, it can be a mess. The only thing you have to remember is that when you choose an arrow direction, it's going to choose which direction it's going to choose the order of these terms, right? And so let's say, for instance, that I reverse the arrow on this one, right? And so let's say that I put this arrow going out like this. And so now, first of all, this term now is going to be on the other side of the equation because now it's going to be Q out. And instead of sigma T1 to the fourth minus J1, you're going to have J1 minus sigma T1 to the fourth. Right? And so that's why I said, all the signs are going to cancel out, because if you swap the arrow direction, then it's going to show up on the other side of the equation, but you're also going to change the signs of the subtractions as well. And so, I think, for most people, I think it's easier just to draw all the arrows in one direction. And so you either point them all in, point them all out, and then just kind of base your equation on that, because all the signs will work itself out in the end. Yeah, so I do it all in, but you can do it all out as well. And so, as long as you're consistent with the signs and how you set up the equations, then it doesn't really matter. Okay. All right. So let's go ahead and solve for the view factors. Okay. All right. right, so first thing we know is that surface 1 and surface 2 are flat surfaces, right? And so we know that F11 is equal to F22 is equal to 0. Okay. All right, so we can get that from just from inspection. Okay. Another thing that we'll do is we're going to form our completeness rules here. Okay. Okay. So what we can say is that F1 infinity plus F12 plus F11 is equal to 0. Okay. And same thing for 2 as well. So F2 infinity plus F21 plus F22 is equal to 0, or equal to 1, excuse me. Getting ahead of myself here. Okay. These are equal to 0, right? And unfortunately, that's about as far as we can take it right now, because you know, usually the way that these problems start, or the way that you can kind of start using these rules, is you need to compute the first non-zero view factor. Okay? Okay. Once you have the first non-zero view factor, then a lot of the others just kind of fall into place using our usual rules, right? So either using a reciprocal rule, completeness rule, or by inspection. Okay. Okay, and so for this particular problem, you know, there's no way we can get a non-zero view factor, because this is about as far as we can take it using our usual rules, right? So using inspection, using completeness, you know, this is about as far as we can get, but it's not enough information to find the first non-zero. Okay? And so the first non-zero view factor here is we're gonna compute is F12. Okay? Because what do we know about surface 1, surface 2, right? Surface 1, surface 2 here are basically two parallel plates separated by a fixed distance. Okay, and so this is one of the geometries that's given to you in the table in the book. Okay. And so this formula, if you remember from last time, this is one that we actually wrote in class. Okay? So this is going to be F1 or W1, excuse me, W1 plus W2 squared plus 4 raised to the 1/2 power minus W2 minus W1 squared plus 4 raised to the 1/2 power. This is divided by 2W1 where W1 here is the ratio, so the ratio of the length of surface 1 divided by the distance that separates them, okay? And W2 is the length of surface 2 divided by the length that separates them. Okay. And so in this case, both the L's and the H's are 1. And so we do 1 divided by 1, we get W1 is equal to 1, W2 is equal to 2. Okay. And so what we get is F12. You plug in all the numbers for this, F12 is equal to 0.414. Okay. All right, so now that we found the first non-zero view factor, we can go ahead and plug this into our other equations, right? So first thing we can find out is we can plug F12 into our completeness rule to find F1 infinity, okay? So we get said that F1 infinity is equal to 1 minus F12 . Okay, so we take 1 minus 0.414, and what we get is 0.586. And so the last one we need is F2 infinity in order to fill in our equations, okay? But, so typically the way that you would do this is you would take F12, you use that to find F21. So F21 here would be A1 divided by A2 times F12, okay? Then you would take F21 and plug it into this completeness formula here as well. But what we can say is that because surface 2 is pretty much identical to surface 1, then by symmetry, or by or you can call this inspection as well, we can say that F2 infinity here is also 0.586. Okay. Okay. All right. Now that we have the view factors for everything, now we can go ahead and plug this back into our equations, equations 1 and equations 2. Okay. Okay. All right, so let me go ahead and write out those equations. And so equation 1 becomes 93,166.41. Okay. Question, so can I explain why F2 infinity is the same? Sure. And so it's because surface 2 here has the exact same geometric dimensions as surface 1. And its position relative to the environment is the same. So what I said is that we have basically a symmetric situation. And so we said surface 2 relative to infinity is the same as surface 1 relative to infinity. And so they must have the same view factors. Right? So I know the temperatures and their surface properties are different, but geometrically speaking, they're identical. And so that's why I say F2 infinity is the same as F1. All right, so we have 93,166.41 is equal to 5J1 minus 0.414 J2. Okay. And our other equation will be 11,291.61 is equal to 2.5 J2 minus 0.414 J1. All right. So we are just about out of time, and so I'm going to assume that you guys can solve this equation. We did one example of this earlier, and so if we solve this system, then what we get is J1 is equal to 19,277.14 watts per meter square, okay? And J2 is equal to 7,708.93 watts per meter square. Okay. And so we obtain these numbers by solving the linear system. Okay. All right, and then really quickly before we go, now that we have the radiosities, we can compute the heat loss of the environment. Okay. And so Q loss. Okay. So the heat loss of the environment is going to be the radiation heat transfer from surface 1 to infinity. So that's going to be Q1 infinity plus Q2 infinity. Okay. And so Q1 infinity is going to be J1 minus J infinity divided by the resistance between them. So 1 divided by A1 F1 infinity plus Q2 infinity is going to be J2 minus J infinity divided by 1 divided by A2 F2 infinity. Okay. All of these are numbers that we have, and so these are all known. And so if we compute that, we get Q loss is equal to 15,275.57 watts. Okay. All right. So I know I went over time, so thank you guys for being patient. And so are there any questions on this before we wrap it up? Yeah. You could usually, yeah, they are in they do follow the same rules of series and parallel. But here often we have such weird circuits with these radiations, and we kind of ignore those rules. And so we kind of just take them individually. Yeah, because for this one, we don't really have any series of them. It's a little bit hard to say. If it's just two surfaces, you can do that. But for this one, there's kind of too much going on. So you kind of just need to take it individually. All right, thank you, everybody. So that's heat transfer, and so that's all the content that we have planned for the class. And so Wednesday we have a review session. So please make sure to vote in the poll before Wednesday. And then Wednesday we'll review, right? So thank you everyone for coming today. If you haven't had a chance to pick up your midterm 2, I have them here. If not, I'll see you guys on Wednesday. Yep.
Those three circuits or resistors in the middle form a triangle shape.
Yep.
If you wanted to, for some self-heating reason, could you perform a Y delta transformation the way you can with electric?
Sure. Yeah.
Huh.
You could. There's no reason not to, but well, the reason not to is that you're not masochistic.
Yeah.
But you could. Yeah. Everything that you learn about circuits can be applied here. Sure. Yep.
Okay, so
Yep.
the picture shows that I was reading and statement.
Oh.
So I took it.
Oh, I see. That's true. So the other version of the exam, it was kind of turned this way. So but I forgot to change that wording.
Okay.
Well, you make up a good point. So that was confusing. So
Yeah, I just wanted to know the future reference.
yeah. So yeah. If you're not sure, definitely ask me. But I would definitely refer to them. Because what I do for the different versions of the test is I just try to change the image about a little bit, but that is confusing. So if you want to give me your exam, I can give you some extra points.
I mean, it would be like extra. I don't know. I just
Okay.
wanted to make sure.
Okay, yeah. So if you're not sure, definitely ask me, and then but the image is you can follow that for sure. Yeah. Mhm. Yeah. Sure. Let me, if they have questions about foresight, let me answer that first.
Okay, yeah.
What's up, guys?
Can you scroll down real quick?
Oh, yeah.
And then we just want to make sure everything's good for Monday.
Yeah. Monday or Friday?
Friday at 10. Sorry, Friday at 10.
Yeah. So I sent you guys an email today. So I booked a room. So it's going to be CS 506, and so that's same floor as my office. It's just one of the contacts. So yeah, we're good. I mean, I just have to. I'll have the exam written. I haven't started writing the exam, but I'll have it done by Friday for sure. But yeah, everything's good. Cool.
Thank you.
Yep. Ryan, did you have any questions? You just want to scroll down. Yes, yeah, 0.93. All right, what's up?
So I think I told you that for 6B, my design proposal was for free convection.
Yeah.
And I've decided to, my parameters to be temperature and velocity.
Okay.
So my input is the temperature, output is velocity.
Okay.
And Dr. Mayer said that we can measure velocity using a hot wire,
Okay.
which measures energy as fluid motion.
Yes.
And then you convert it using something called King's law to velocity.
Yes, I've heard of it. Experiments are definitely not my forte, but
Right,
I've
yeah.
heard of it.
Yeah, I was just having trouble wrapping my head around how to vary the parameters exactly. So our heat influx, should we keep it constant or should we vary it?
So it depends. And so if you want to measure, if you want to measure the effect of like, how much faster the fluids will go, depending on how much heat, and you should change the heat flux coming in. Because the heat flux coming in, that's going to change the temperature of the plate.
Right. Oh, and yeah, sorry.
And so I would do a couple. So I would definitely, I mean, if the way that you can control it is by controlling the heat flux coming in, I would also have a thermometer or a thermocouple on the plate itself.
Right.
So you can monitor the temperature of the plate. Because those things aren't usually one-to-one. So if you control the heat flux coming in, you should also know what temperature the plate is at. So that's one thing. So you can see how, and that would be just a thermal conduction. Because of how much heat you're putting in versus the temperature of the plate depends mostly on thermal conductivity of the plate, as well as the heat loss that's coming off as well.
Well, I was thinking to keep it more one-dimensional, just focus more on the velocity aspect. Which I guess,
Yeah, you can do that too.
we can say that the thickness of the plate is negligible.
Okay.
Let's say conduction is negligible.
Okay, sure.
That's what I was thinking, but,
I'm assuming you're heating it from zero vertical.
I think we're gonna do horizontal.
Horizontal, okay.
Because we brought up some points, we're gonna do vertical, we brought up some points.
Or the same thing.
Yeah, it definitely.
Something like that.
Oh, okay. Oh, I see.
I mean, both motions.
Yeah.
Something in the type of like unbalanced motion.
Uh-huh.
So, yeah, I think we were just gonna measure the velocity of the. So.